When it starts to get with Ocean's window, otherwise there's a sound that is
Okay.
backwards. That's important. So we notice it. You're online. All you have.
Okay. Shall we wait a couple of minutes or? Well, it's time, so let's start. I think we can start now. So welcome to today's talk of this STEM week. It is my pleasure. It is a really big pleasure to introduce. Oh, sorry. Yes. I'm here. Okay. I'm not used to being on the spot like this. Like this. Okay, so thank you very much for being here. Welcome to this talk of the STEM week. And I was saying that it's my big pleasure to introduce Professor Dr. Luis Arturo Godínez Mora-Tovar. And I'm going to tell you just some details about his academic career, because he has a really extensive curriculum. So I'm going to focus just on a few details that are relevant. So Dr. Godínez was born in Mexico City, and he graduated as a chemical engineer from UNAM, where he obtained also his degree in chemical sciences in physical chemistry, specializing in physical chemistry. And then he obtained another 2 master degrees, one in chemistry by the University of Miami, and one in commercialization of science and technology in a joint program with the University of Texas at Austin. In 1997, he graduated with a PhD in physical chemistry from the University of Miami, and later he did a postdoctoral stay at the University of South Florida in the United States. During his studies as a bachelor, he received academic, he received some prizes like the Gavino Barrera Medal for his studies, his master's studies at UNAM, and other academic merits. Later, after doing his postdoctoral studies, Dr. Godínez came back to Mexico, and he started working in CIDETEC, the Centro de Investigación y Desarrollo Tecnológico en Electroquímica de Querétaro, in 1998, where he developed as a researcher in human resources formation, and also in very important academic and administrative work. In December 2005, he was named General Director of this CONACYT Research Institute, and he stayed as the General Director for 10 years. After he finished this commitment as General Director, Dr. Godínez went to to be Science Director, right? Science Director in CIDETEC. And in March 2017, he moved to Mexico City, where he became the General Director of the Sistema Nacional de Investigadores of CONACYT. Since June 2021, Dr. Godínez is a researcher at the chemistry faculty at the Universidad Autónoma de Querétaro. Besides his academic career, or I mean, it's part of his academic career, he has 6 patents, 6 patents, and he has done research work that accounts for 154 publications in refereed papers. For those of you that know the value of the H index, he has an H index of 36, which is really impressive. He has more than almost 4,000 citations. Since 2004, is member of the Academia Mexicana de Ciencias. In 2003 and 2005, he was named Vice President and President of the Mexican Society of Electrochemistry, where he remained until 2007. In 2018, he received the National Prize in Electrochemistry as in recognition of his contributions to the development of electrochemistry in Mexico. Since 1999, he's a member of the Sistema Nacional de Investigadores, and since 2010, he has been distinguished with the maximum level, the level 3 of the Sistema Nacional de Investigadores. Well, a very important part of a researcher and an academic as Dr. Godínez is also transmitting this knowledge and this passion for for research and learning to others, to students. So in the formation of human resources, Dr. Godínez, well, he has been a professor, a teacher in different institutions, in the Autonomous University of Querétaro, in UNAM, in the University of Miami, in CIDETEC, and in ITESM, in Campus Querétaro. And as an academic advisor, he has directed works for bachelor degree thesis for the undergraduate level, master degree, and PhD, accounting for 4 students in for bachelor degree, undergraduate thesis research project, 19 master degrees, and 4 PhDs. And it's worth mentioning that of all his PhD graduates, all of his PhD graduates are part of the SME. 2 of them are in the level 3 also, in the highest level in SME, 3 in level 2, and the others in the level 1. And here I have to mention also that I was lucky enough to be one of these numbers here. I was one of those 4 students from that did his undergraduate thesis in his lab. And with this, I want to finish, but I want to mention just briefly my experience working at his lab. That was a really life-changer event. It's where I gained part of the motivation that led me to be here at this moment, to continue a career in research and academics. So I hope that we all can enjoy this talk and that we can take advantage, because I know that he inspires and he can lead you into, by inspiring you into a very exciting and rewarding career in science. So let's thank Dr. Godínez for being here. Give him a round of applause and hope we enjoy this talk. Thank you very much. Oh, yes, sorry.
Well, thank you very much. Thank you very much, Jesus, for this very nice introduction. Thank you very much for the invitation to be here with you. I'll try to talk a little bit about what we have been doing for the last 20 years in research. Can we set up the presentation? I apologize in advance for my English. It's very rusty, 20 years since I haven't been practicing, but still I'll try to convey you the ideas. Okay. So we have been working on what we call electrochemically advanced oxidation processes. Electrochemical advanced oxidation processes are processes for water purification. So there are new technologies for water cleaning. Okay, the next one, please. So what distinguishes these processes is the use of a very powerful oxidant species, chemical species, which is called the hydroxy radical. If you can see in this table here, you can observe in the right side column the formal potentials for different species. The higher the value is, the more oxidant it is. So it's a species, hydroxy radical, as you can see there in the red row, is one of the highest. It's just below fluorine. Is more powerful than ozone, than hydrogen peroxide, than permanganate. What that means is that when this species finds any contaminant, any organic material, it goes for it and oxidizes it. Now, there are many ways or different ways in order to produce this hydroxy radical. You cannot buy it in a bottle because it's extremely reactive. Therefore, it reacts with everything. So you have to prepare it in situ in order to clean up the water. And there are many ways to prepare it. One of them is the Fenton reagent or the Fenton mixture. The Fenton reagent is the mixture of hydrogen peroxide and iron 2 ions. That's this mixture. When these 2 species interact in water, as you can see there, they produce the hydroxy radical, and this hydroxy radical can react with the pollutants in water and basically burn the contaminants. That's the idea. So as anything else in life, the Fenton reagent has different advantages and disadvantages. I'm going to talk a little bit about some of those. The advantages that we find with the Fenton reagent is that, as I was mentioning, it has a very high oxidation power. So it's non-specific. You can use it to clean up everything. It's suitable then for contaminating microorganisms and for effluents with pollutants that are toxic toward the microorganisms that are usually employed for cleaning up water. So when you use your biological plant and you get water that still has some contaminants or contaminants that are toxic to these microorganisms, you can use this process. Now, it has several disadvantages, and you cannot see at this point in time plants using the Fenton reagent, water treatment plants using the Fenton reagent. And the reason is that hydrogen peroxide solutions are expensive. Hydrogen peroxide is a material that is expensive, difficult to handle. It could be even dangerous if you don't handle it properly. And you have to maintain a concentration of iron, a concentration of hydrogen peroxide to have the reaction, and you have to monitor all that, and that is costly. In addition, this was a pH 3, which is a little bit acid. So you have to put acid into the water. And then when you end up your process, then you have to neutralize that acid and eliminate the iron. And when you add up all these things, well, it's not very convenient. So when we compare, just very roughly, the characteristics of a biological, a physical chemistry, or the Fenton reagent approaches to clean up water, we can see that it has some very nice advantages that you can see here. For example, it requires small spaces. It has a high oxidation power, so it takes care of everything. It's fast. So it's better in general terms than all the others, but it has these two red squares here, which dominate, let's say, the criteria. It's not safe, and the costs are high. So that's the reason, or some of the reasons, that haven't been used. So what we wanted to do is to try to solve those problems using electrochemistry. Electrochemistry, in very general terms, is the part of physical chemistry in which you use electricity as electrons in a current as a reagent for reactions. So what we do is that in a cathode, we could inject electrons, and the oxygen in the solution could be used to produce hydrogen peroxide. So you don't have to buy it, you don't have to administer it, you have just to prepare it in situ. That would be one advantage. The other one is that if you're putting electrons there, you have to be taking them out from here. And in this anode, you could use materials to oxidize water and produce more hydroxy radicals. And actually, you could use anodes, which are semiconductor materials that you could use with light in order to improve the performance of the reaction. And well, it has also a problem, or as I mentioned, we need to add acid for this reaction to take place, and we need to add iron, and then we have to remove it. So that's like the big picture of the problem that we started to work about 15 years ago. So the very first thing that we wanted to try was to see if we could produce hydrogen peroxide using these reactors. That is that reaction to specifically reduce oxygen to hydrogen peroxide in the presence of iron. We put iron. And then we prepare this first reactor. As you can see here, we use a glass tube, titanium dioxide, it would be the anode. We put a UV lamp to promote the reactions in the anode. We use a carbon cloth around the tube, and we pass the water between the electrodes. And then we put some electricity on it. And then we began to do experiments that was back as far as 2006. You can see here that if we measure the hydrogen peroxide concentration as a function of time, we began to see how it increased, but at some point, the rate at which the hydrogen peroxide is produced is the same as the rate that the hydrogen peroxide is consumed. So there was a problem. If you produce it in the electrode, it stays there and begins to decompose. So what we did is that we changed the reactor, and we went into a process in which we use electrodes that are permeable to the flow of water. So the water goes through the electrode. As soon as the reagent is produced, there is removed because the water is going through them. We put the UV lamp here, and we have electrodes. Again, the cathode is a carbon cloth, and the anode is a carbon cloth covered with titanium dioxide. And with this arrangement, we could prove that actually we were preparing the Fenton reagent in situ with electricity, which is the very first thing that we wanted to do. Here you can see the decrease in color of a solution. You can see there in photographs, you can see here in data, in analytical data from absorbed measurements. You can see that when you only have electricity, you have this decrease. When you only have light, you have this one. When you have electricity and light, but no iron, you have this one. And when you have the Fenton reagent, you have this one, which is faster. So we were seeing that we were producing this Fenton reagent electrochemically in the reactor. That was one problem. The second problem, as I mentioned, was one more, please, was the iron, was this one. The problem here is that you have to add the iron, you have to let it react and then you have to remove it. And then following a report from an English group, Kiwi and coworkers, they use Nafion membranes. Nafion membranes could attach cations. So they use a Nafion membrane, they put iron ions there, and they use it to do the Fenton reaction. So we did something similar, but we didn't have enough money to buy the Nafion, which is very expensive. So we bought resins, plastic resins that are cationic exchange resins. So the commercial name is Purolite, and I don't see it here. I'm going to show you later. But the idea is that the resin has the iron atoms attached to it, the iron ions. So these ions are in equilibrium, and the resin is releasing the ion little by little. So you don't have to have it in solution. It's just a controlled release of ion. So as you can see there, we put the resin here in one of the chambers. And here you can see that when we compare our process with the one with Nafion, ours goes even a little bit better. It's almost the same. So it's working in terms of releasing the ion that you need for the Fenton reaction. And in the graph there, you can see the prices. So it's substantially lower, our price, than the price for Nafion. So we have been working with the iron and with the hydrogen peroxide. And the other nice thing that we wanted to do was work with the anodes. The anode is a semiconductor material, it's a titanium dioxide material that when you illuminate, you produce the reactions that you want. So the problem with these reactors, with photoelectrochemical reactors, is that you have to put a lamp. The light has to go through the wall of the reactor, has to go through the solution, and then reach the electrode. And you have then photon losses along the way. So the idea that we wanted to pursue was to use optic fibers. Optic fibers are, excuse my analogy, are sort of a light hose. It's a light hose. So it's a hose, the light goes through it. And if we make holes along the hose, if we attack it chemically, this was titanium, silicium oxide, that's glass. So we put them in hydrogen fluoride. So we made holes on it. And then light can escape through the holes. And if we put titanium dioxide, the semiconductor, then we're activating, we're illuminating inside the electrode, inside the tube. And we could have the reactions going. So what we did is that we prepared these optic fibers. We modified them with different amounts of titanium dioxide coating. And we could observe that there was a maximum of hydrogen peroxide production here with 5 coatings. If you put too much, the photons and everything happens before getting into the water. And if you put too little, then you don't have it. And here you can see when you compare the different arrangements, if you illuminate from the outside, just the lamp with the electrode, or from the optical fiber, you could see that works pretty well. So we are using a photo illuminated. It's an interior photoillumination from this anode. Well, we have been working on this study, this is research, we're publishing this. And then we wanted to go into some applications. I'm going to talk to you about how we have been using this in 2 applications that we feel could have some potential for technology. The first one has to do with activated carbon. As you all know, activated carbon is the material, the most used material to clean water. So you pass water through a column, a packed bed of activated carbon, and then basically all the contaminants get absorbed into the carbon material, carbon particles. You can find these packages in a very large sizes for companies, or in very small ones for your refrigerator, or in your kitchen, or in different appliances. We have activated carbon. Well, activated carbon particles have pores, have channels. They absorb these contaminants. And as you can imagine, eventually they get saturated. So you have your filter doesn't work anymore. You have to call up and they recycle. The way they recycle it is that they take the activated carbon, the used or the wasted activated carbon, and they regenerate it. And there are 2 ways. One is thermal treatment. That is, they heat it up and all the contaminants sublime. So you evaporate the contaminants. And the other one is called solvent extraction. And solvent extraction basically means that you wash it with another solvent. So what we do is that you use the solvent, and the solvent takes up the contaminant, and now you have the contaminant in the solvent, not in the carbon, but you separate that, okay? And the most important part, no, the most important part, gracias, is that you have to take it into a plant to do that. So you cannot do it in the place where you are using. You have to put everything together and take it into a recycling plant. And that's costly. So what we try to explore was the idea, carbon is a conductor material. It conducts electricity. So if you have an activated carbon packed bed, particles compressed, they could conduct electricity. And if they can conduct electricity, then they can be an electrode. So taking that into account, we made some experiments putting different densities of carbon and trying to find out with these electrical circuit simulations that we did, this technique called impedance spectroscopy, to see which were the conditions in which this would behave like an electrode. Then we were changing, compressing the package and measuring the conductivity, and found the conditions in which this thing behaved like one electron, a tri-dimensional electron. We actually measure the concentration as a function of density, conductivity. We measure the concentration of hydrogen peroxide generated. So using this as a cathode, that's just exploring the idea. And then we went into the application. We figured that if you had activated carbon that is already wasted, covered with the contaminants, we could put it in contact with an iron-loaded resin. This iron-loaded resin will be in equilibrium with iron, and if you inject electrons into this material, then you can reduce oxygen. The oxygen would produce hydrogen peroxide, with iron would produce this OH, and this OH could clean up the contaminant in situ, the material in situ, the adsorbent in situ. So in order to try that idea, we built up a reactor. And basically what we did is that we had a granular activated carbon mixed with the resin loaded with iron. We put a counter electrode, a measurement device, a pump, and we would pass water through it. Every 30 minutes, we would put toluene solution and look how this toluene solution, the concentration, would be at different points in time here in the water. So as you can imagine, when we don't do anything, not treatment, just the carbon packed bed, we do 3 additions. So carbon takes off the toluene, and after the 4th one, it has taken everything that it can, and then you begin to see a linear increase in the concentration of toluene. That's okay. Then we put electricity and nitrogen, so no hydrogen peroxide can be formed, and it's more or less the same. Then when we put the oxygen and electricity, so we put hydrogen peroxide, it's still the same. And then we put the resin or the iron, and then we don't see the toluene again. So you take it into the carbon, so the carbon absorbs the contaminant, and then the electricity takes care of everything, and it cleans it up again. And then it's working continuously. In fact, every addition that we make of toluene should account for more than 200 parts per million, and we never see more than 20. So it was working pretty well, and this is one of the patents that we applied for. It's a regeneration method for carbon. Now, one thing that we didn't understand very well is how is it that it was working very well? Because you do the regeneration cycle, and it seems that the carbon works well. So we compare our system, which is let me see, which is this one. We compare with the other 2 common industrial techniques, the thermal treatment, the solvent extraction system, and only the Fenton reaction, not the electrochemical Fenton, the Fenton reaction. So we compare everything. And as you can see in this result that we did about 6 or 7 years ago, we observed that our system, which is with these red dots here, has far better regeneration than the other systems. In fact, thermal doesn't count for more than 5 cycles because you burn it up. And the reason is, well, we didn't know that. The truth is that we didn't plan this. We just found it. But the truth is that it works like a polarization protection effect. The way you protect, for example, power plants and the boats, no, when they are metallic from corrosion, that you impose a current. And if you put a current, they don't oxidize. We were putting a current in the carbon. So we were protecting it from oxidation. And that's something that was good. And as I said, was not planned. Gracias. So at the very end, what we wanted to do is to compare our technology, our new approach, electrophoton approach, in terms of activated carbon regeneration when compared to thermal and solvent extraction methods. And as you can see, compares pretty well because it's safer, it has lower operation costs. You don't have to remove the pack, so you can clean it up on site. And we are foreseeing applications of this in filters and water for drinking water, for example, in schools and things like that. Well, that's one of the applications that we wanted to talk to you about. The other one has to do with the toilet. And this one is related to the fact that, well, if you look at the research, 80% of the research in water treatment is carried out assuming that contaminated water gets into the water treatment plant. So somehow the water gets there. The truth of the matter is that for 2,600 million people in the world, that's the third part of the world population, it's a lot of people, don't have drainage. So the fact that you go to the toilet and then you push a button or pull up a cord or pull down a lever and then forget about the issue doesn't happen from one person in every 3. That's a lot. That's a huge problem. Now, if you don't have drainage, then what do people? Well, some of them just don't do anything with the waste, and that's a very big health problem. Some others just contain it. As well as septic tanks, with the translation, you just contain the waste and then you sort of neutralize it until a truck or some company comes along and then takes it into a water treatment plant. But that's a huge problem. So in Mexico, there are around 9 million people that are lacking sanitation services. Well, what we tried to figure as a plan was to develop a toilet that does not need a connection to drainage. It's a small human waste treatment plant. This is not our idea. This is something that the Bill Gates Foundation was financing, was looking for research groups to develop. We participated in a contest and we won some money to develop what I'm going to talk to you about from the foundation. But the idea is that you have your people that gets waste. It's a mixture of liquid and solid. You get into a biological treatment, small biological treatment. Actually, there's already some commercial small plants for that. And then you can get a small amount of solid waste, which is like abono, how to say the word? Fertilizer. About everyone of us in average is produce 5 kilograms of dry solid per year. That's not a lot. But I think it's 14,000 liters of liquid. That's a lot. And that liquid is contaminated. So the idea is that you get the solid you can, with a solar heater, make it innocuous, disinfected, and then you have to disinfect the water. And that's where the problem comes. And that's where we wanted to use our electrochemical treatment. Not to eliminate dyes, but to eliminate pathogens. So we focus on that. And the idea is that if this device, such as that one there, what's just that drawing, does not need the drainage and does not need the electric power connection either, because it could work with solar cells, then you could have a device that gets rid of the huge investment that is implied in putting drainage to the people alone. Okay, so we work on that. Okay, so why it was a good idea? Because the Fenton reagent, as you can see, can eliminate some of the most dangerous pathogens that there are. There are some pathogens that are easy to eliminate or easier to eliminate, and there are some others like helminth X or helminth ova, which are basically pathogens that have very resistant membrane. You can see there how after some time the Fenton reagent destroys the cell. It goes and attacks, as I said, attacks everything, or attacks the membrane. So we wanted to do that with our reactor. The first thing, of course, we just proved activated carbon. That's what we call adsorption. Then we put electricity in the absence of iron, just electricity across this carbon to see if that works, because that would be great, no? If you could do it only with that. That we call EO, which is electrooxidation. And we tried first E. coli solutions, as you can see, of course, as expected, only with adsorption. You don't see any elimination, everything's there. Distributed along the reactor. These are different parts of the reactor, different zones of the reactor. And when you put electricity, you get rid of E. coli at the outlet, at the last part, okay? As expected. Now, for helminth ova, which is far more resistant, are more problematic, then of course we don't see almost anything. So we cannot do anything. You can see in dark and light color bars the viable and non-viable pathogens. Of course, what we want is non-viable. So the conclusion of this is not working, no? Like only with that, obviously. Now, we wanted to do electrofenton, not only electricity and not only adsorption. We wanted to do electrofenton, but the problem with electrofenton, if you remember, and this is the most important problem, is that you have to add acid, you have to add iron. So here you would have to have a toilet in which you add iron, you have acid, and then you get rid of iron, and you get rid of acid. That was the problem. So this is what we figure out how to do. We prepared a reactor, or we conceived a reactor, and we have activated carbon packed. We have the two electrodes, so you polarize, you do electrochemistry here. But then before, you put the resin, this resin, loaded with iron and protons. So the water washes out the iron and the protons and gets that into the reactor. Now you have the conditions here. Then you do the electrochemistry, you clean up your water. The water, of course, keeps coming, and eventually will wash out the iron and the protons. But we put another resin here, and that resin now traps the protons and the iron. And you end up with clean, neutral water. Obviously, if this keeps going, eventually you wash this out, right? So what we had to do is figure out a time in which that stops and then change the direction of everything. If we could change the polarization in the direction of the flow at this time, then we would have the iron and the protons all the time inside the same reactor. So that's what we did. At times larger than that, now it goes in the opposite direction. You recover the iron, you recover the protons, you get them into the other resin, which is the first one, and then you do this independently. That was the idea. Well, that's nice in PowerPoint. Now we had to try to get it into the reality. So what we had to do is to measure how iron and how protons go across the different chambers of this free compartment reactor. I'm not going to go into the details of that. I'm going to show you that we could measure the hydrogen, that's pH, the iron concentration at different times, and then arrange or find out that every half an hour, if we do this switching, everything was contained inside. And then, as you can see here, we could maintain these conditions of performance of the electrophoton reactor for a die, only for a die, because that was the concept. We published the concept. Well, just recently, the concept in when we don't do the recycling. So it worked out. Now that's nice with a die. Now we wanted to do it with the pathogens. So we prepared the reactor. The idea is that here you have the resin. You have the resin loaded with iron and with protons. You have activated carbon here. You have electricity here. As I mentioned before, the resin releases iron. And all the reactions that I already talked to you about occur or take place here in the central compartment in order to clean up the pathogen. Since we would be recycling the water in different directions, then we would be mixing everything up and cleaning all the compartments at the same time. That we call electrophoton, which is applying recirculation, or electrophoton recirculating in this, and thank you. And this is the important one in which we do a step of absorption and a step of recirculation, absorption, recirculation. That means that we are keeping the iron and the protons most of the time inside the reactor. And then, well, when we do the E. coli, that as I mentioned, is the easier one to deal with, well, under some conditions, we still see the pathogen, but this is the important one. This is the one I was talking to you about, and we don't see it at all. Well, that's E. coli. That's not the most important. Now, for Hamitex, which are the important ones, we also didn't see it, as you can see. Everything was destroyed, and you could see that here's the last graph. Here you can see that helminth egg inactivation and percentage is complete when we use this operation mode as compared to the other ones that we were testing with the same reactor. So we had the electrochemical reactor, and then with funding from the foundation and from CONACYT, we build up a toilet. Here, this is the first version, the toilet 1.0. And then you have a hole here, down here, and that was lab, which is that one. So down there, we had all the pumps, the compartments, the tanks, and we were proving, or we're testing different flows, different arrangements, the electronics, etc. And that was our first prototype. Then, once we had all the conditions for operation, we went to a company, an engineering company, product design company, and then one more. And then we build up this one, which is our last version. This one is has been working for over a year now in the main building at this research center. This is outside the building. There is a pipe here that connects to the toilet, which is inside the library. So it's working with real human waste. And so far it's working fine. So we have the 2.0 version, which is a toilet that works without connection to the drainage and to the electric power. And the disinfection is electrochemically based in advanced electrochemical process. So what are we after after this talk that I have been showing you? Some of the things that we're doing, we're trying to get this fourth column here, in which electrophoton approach solves or is better than some other approaches in terms of the electrophoton. Reduce the safety. When we use electricity, we don't have to deal with hydrogen peroxide solutions. And when we deal with operation costs that are low because we're not using acid, we're not using iron, we are not neutralizing and we're not removing. We have been doing, we are working some applications. This one is a nice one. For example, the reactors that I'm telling you about are here inside these tubes. So these tubes are actually the floating devices of a small solar cell. So you have this thing floating on a lake or body of water, and then it moves because it has some hélices. Yeah, propellers. Thank you. Propellers. So it has some propellers. The water gets in, the whole thing moves, and the water is going through the tube and it's being cleaned up. So it's cleaning the water surface, and it's working with with a solar cell. Or for a company, we are developing a series of reactors. So we're trying to use this for different applications. Now, I'm not going to go into details. What we're doing right now is that we're trying to develop 3 big electrochemical reactors. And this is very nice because everything in electrochemistry takes place in the water electrode interface. And everything in the middle is space that is sort of wasted. So we could develop a system, a reactor in which the surface, electrode solution surface, you improve. So what we're doing is that we're using these activated carbon packed beds as the cathode. This is the cathode. We could use a container, which would be an optic fiber, like a wire is getting into this packed bed. And we could put light inside here and have the anodes here. So that's what we're doing. We're doing some kinetics, we're modeling what the reactions, adsorption, Fenton, and electroxidation reactions. And then we're trying to get values of the constants, different arrangements, etc. And that's what we're trying to do now. So this is work that has been done for many people, many students. As you mentioned, Jesus was one of them many years ago. And then, well, most of this work has been done in this research center. Now we're extending the group. Now we are also in the university. And well, that's the first institutions that have to be acknowledged. Also the funding agencies, the CONACYT, of course, the Gates Foundation, the Electrochemical Society. And obviously, I want to thank you for your attention, for your kind invitation. And I'd be glad to answer any question if I can, of course.
Okay, let's start by thanking Okay, so now it's time for questions. I know that you should have like many questions. This is a project. I want to point out one thing for the students here. If you notice when the talk starts, the dates of the publications were around like 2004, 2005. So 2006 already. And then the last one is from 2020, 21. So, and it's an ongoing project. So science takes time. Good things like this take time to do. This is something that spans already 14, 15, 16 years, I guess. How old were you 16 years ago? So it's very nice to see this here. It's very nice to see these results, a nice story, but it takes a while of time and a lot of effort from students, postdocs, researchers, ideas, trying to find funding and things like that. So it's very nice, but you have to think that this is the result of really a lot of work that has been involved in developing like ideas and bringing ideas into reality. So with that in mind, I invite, well, first the students. I don't want to restrict our faculty, but I would like to take questions from our students first. Oh, yes. Also for the ones in Zoom, if you have questions, please open your microphone, and I'm pretty sure Dr. Godínez is going to be really glad to answer them. Okay, we have a question there.
Well, I am curious. Okay, I am curious about how are you assessing the development of the toilet that you have already, the one that you show us in the picture, because you told us about that you were going to look for the T1 or the time that the resin was like kind of born out or used. So how have you been assessing? Okay, it's time to change it, or are you going to change it, or what's what will happen with that?
Dimension everything. That's what you. So what we would, of course, there are degrees of freedom here. You can design a very small one, no, the most active one, or you could have. Or, for this one in particular, we calculated what would be the human production, average human production for 4 people. And then we figured that you have to deal with about 90 liters per day of water. And then considering what is the residence time in the biological process, which is the slow one, then we could dimension the whole biological thing. And then with that flow of water, we could dimension the electrochemical.
So, for example,
Mhm. Exactly. This one is for 4 people. And actually, this one, we put one electrochemical reactor and it was working very well. And then we put the second one in series. And if we need more, because the water that we're getting out of this now is good enough in to watering purposes. So it could go into the environment, but you cannot drink it. Or it's not for human contact yet. If we put 2 or 3 or 4 disinfection systems, and maybe it could be drink water. Maybe not yet, no. So it depends. You have to take some decisions how you dimension everything.
The urine for the pH that you require for the mechanism that I mean it will go through and there are different pHs. Is there a limit of how acid can it be or it doesn't matter?
For yeah, sure. For the whole the whole biological treatment is close to neutrality, close to pH 7. Now, when it gets into the electrochemical treatment, it cannot be pH 7. And the reason is that the iron at pH 7 precipitates a hydroxy compound. So you need to acidify that, which is what happened. So we acidified it with the resin. But the acid conditions, the acidic conditions, the low pH are only inside the reactor. Once it comes out, it goes out neutral. And that's one of the things that we believe are attractive for this approach, because you don't need to add the acid. And you don't need to add the iron. Everything is contained inside and, let's say, steered down there.
More questions?
Is there a limit of cycles that can be done in this specific case?
Yeah, sure. There has to be a limit. There has to be a limit because it's not a perfect process. We calculate about 30 minutes and there actually could stay there 45 minutes. So we shorten it to 30 so that most of the acid and the iron remains inside, but still some of it is coming out. And there was no way to calculate that. So that's why we built it up and are trying it, and it has been working for over a year.
So 1 year we haven't done
any kind of replacement of things. Now, the truth is that this is the pandemic conditions, which also the use is very, so it's not, let's say, regular condition. There are people working there, but not the same pace that you would expect for us. So the truth is that I don't have an answer to your question yet. Not yet. But we are measuring it because we understand that we have to measure. They have asked us for the cost, the maintaining cost. The truth is that most of it is the investment cost because you don't do almost any maintenance. We will have to change the resins, the acid and the iron, but maybe every year. And if that is so, it's very low as compared to the investment cost.
And one of the carbon, the activated carbon, is there also a number of cycles? Can we change the carbon, reduce waste, or?
The truth is that that should last far more. For what I presented before. When you use this carbon is being, well, is working as an electrode. but you are changing the polarity all the time. So the right part is cathode, and the right part then is anode, and the left part is cathode, and then is anode. So you are putting electricity into it, and you're protecting it from corrosion, which would be the degradation mechanism.
And the quality of the water that is coming out is the same, usable for laptop.
Is
You trying it to use it in the lab? I'm thinking about it could be one of the water treatments that can be used in the lab instead of using that. Yeah, water or something.
yeah, if this water, there are norms. So if you account for certain limits, then you can throw it away into the drainage.
Sure.
If you account for certain limits, then you can use it for watering purposes. Another limit is for human contact, and the last one is drinking water. We are in the second one so far. So we can use it for watering purposes. And if we put more disinfection and polish more the water, eventually we could get it into human contact or to any application that you. But this is water coming from human wastewater. If we have been doing some other waste, for example, we did something for tequila waste. So it's different kind of inlet water and different kind of effluent and different. So we can, as we were dimension, I think, according to the inlet and outlet conditions of the water.
Really
Thank you. It was a great talk. The topic was amazing. And also the way in which you presented it was great. Um, I do have a question regarding cost, because you do mention that investment is like a big number from what I can tell. Do you have a bit of an approximate of that number?
Sure, I can tell you the approximate. I can tell you a number, but I would like to say something before the number. Like in any, well, almost anything, the first prototypes are extremely expensive. If the first plane that was built is extremely expensive as compared when you build them in series. So this one in particular was about 600,000 pesos, this final prototype. Well, it's
No, I mean, from the context
right,
of
right.
the technology.
Right, because this is a stainless steel. We wanted it to look pretty. And we wanted it to last a long time. And we wanted to take people to sit there 6 months, a year, and don't see everything rusty. And no. But then we went for the best materials. We do believe that if we change this for plastic and from containers that are already available in certain dimensions, because we build everything up to tailor for the design. And now if we do some, it could go down probably to 70,000 pesos or something like that, 80,000 pesos, maybe. And if this goes into a series and gets into a company, because that's something that I think it's very important. We do the science job, the technology development job, but the company has to be another one. Entrepreneurs have a different frame of mind, and then if they do it in series, I'm pretty sure they will make a.
Because you do have like a solar panel attached
To it, right?
Right.
So the electricity required for the functioning of this prototype, I don't have like a margin or idea of how much that is, but I'm assuming there would be leftover electricity, right? I don't know.
We're using that's also a very interesting question, and that's also a question that we have used in order to think of the prototype. Mexico is a country that has one of the higher irradiances in the world. We have a lot of sunlight, so we have a lot of solar energy potential. And what we do in this prototype is that the solar cell, which is commercially available and that's a very mature technology, we charge 6 batteries. So during the day, you charge the batteries, and with the batteries, the system works day and night. And there is some leftover. Well, we calculated the solar panels and the batteries to fulfill these dimensions that I was talking about. But we can always change that, right?
No, I was thinking because there's another perspective in there, right? If you think of an integrated use for a house or for a whatever, right?
Mhm.
You put the solar panels, some of it work for the toilet, some of it for the rest.
And let me tell you, this could be of interest also if you guys want to do later research of these new technologies. Some, and maybe you know this, but well, most of the organic material is treated with microorganisms. Microorganisms eat up the material, the contaminants. But some people are working on putting these microorganisms in electrodes. So when they eat up these things, they generate electricity. So the idea here is that you are getting energy out of the process of this of degradation of organic materials. That's a new trend in electrochemical, in bioelectrochemistry. No, no. So that's interesting because as you mentioned, the idea eventually will be to be integrating everything, to integrate everything, and you get better devices and better technology.
More questions from students?
I was actually thinking about
Yeah. So could there be an application in bioremediation? So for example, bioremediation. So for example, contaminated lakes or something like that. Because I was thinking about how after some time the acid and the iron could actually escape the container. So what could happen?
Sure. The idea here is that they can escape. And there are no large quantities, depending on how the amount of acid and iron you are putting in. But let's say that you have one of these floating devices which are for lakes. Well, we're designing them for lakes. The idea is that this thing would be with the sunlight moving around, and as it moves, cleans up water. Eventually, the amount of iron or acid that is releasing would be nothing, as compared to a body lake. No? But it depends on the application, sure.
I think we have some time for more questions. I have a question. Actually, I have several questions, but I'm not to limit myself. So, well, I'm amazed by all these applications. It's fantastic. And although I appreciate and I admire all these things, I'm always like interested in the fundamental science, and I have to go back to those things. So my first question is about, well, I know that the Fenton reagent works like pretty well in this thing, but like the first thing that came to my mind, and I'm pretty sure that there have been like such things, have it been tried a different metal instead of iron? Because there have to be like other metals that are easily oxidized, reduced, and that can do the same work, right? So any comments on other reagents like Fenton that can be used or could be used, or why they are not used, and we focus only on the Fenton with the iron?
Yeah, sure. There is a whole trend of studies of area of study, which I call Fenton-like. So you're right. The idea is the hydrogen peroxide molecule gets near the iron, and it interacts with the orbitals of iron. And those are d orbitals, and then you have all this, well, you have the production of the OH radical. Well, there are many metals that have this. So there have been studies with cobalt, with manganese, with, well, other metals. They don't work as good as with as iron. So it's Fenton-like, you know? But they have been, and actually there's a lot of people now that are preparing these carbon electrodes, and they are depositing the metal inside the carbon. Iron, cobalt, manganese, or any other thing. If you have waste, you have a carbon waste that has already some metal attached to it, it could work because the metal dissolves there and is close to the surface and is doing the electrophenton right there. So people are preparing different arrangements and architectures, molecular architecture for those. Yes.
Okay. And one last question, and this is about, and I think my students should be interested in this also. It's about the kinetics. You showed us like some kinetical determination that you have, both for the, I think it was for the decomposition of H2O2, and later also for, it was the kinetics of, I don't remember if it was also the production of OH minus or something like that. But can you comment just in general, because this is something that we study in class, Can you comment in general how these kinetic determinations are done? In general, how do you determine these kinetic reaction constants and things like that? Just like,
Let me see if I understood all your question. But then you have a model, a kinetic model. A kinetic model assumes that there is some mechanism for reaction, and then you have an equation that describes that model. So it's a differential equation, then you integrate that, and it gives you the concentration of the different species being consumed or formed as a function of time, right? Well, what we need to do is to measure time and measure the concentration of one of these species as a function of time. So that's the experimental data and the theoretical model. And then we compare them. Usually what we do, and probably this, what we do is that we imagine what would be the possible models, could be 2 or 3 models that describe what's going on. Then we measure that. And then we have this concentration versus time curve, and we feed these 3 models into the experimental data. The one that fits better is the one that gives us the idea of how it goes.
You have like first order kinetics or second order kinetics, and then you have those models. We know the integrated rate laws for those kinetics, and then you fit your data to those. Okay. Okay, great.
Yeah, and
So-
that's how we assume. In some other times, the one or the two. It's a complex process, so we just feed it to a fraction. It's a complex.
The reduction to see if there's if you find like some other complex kinetics that cannot be fit into these integer models of integer orders of kinetics.
Yeah, actually, for most of these reactions, everything that happens is not the first, second, etc. accounts for homogeneous kinetics, right? The species are in 3-dimensional spaces. When you have something on the surface, something that first needs to absorb and then reacts once it's absorbed on the surface, then you have a different mechanism. Electrochemistry is about that. Electrochemistry is what happens when electrons go through an electrode into something from 2 to 3 dimensions. And usually the models are different, are not the same. And they are models. People have worked them out, and they are different.
Okay, so let's thank Dr. Godínez for this very nice talk.
Thank you. Thank you very much.
Thank you very much.
Thank you very much. And for the people that is online and for you guys, 12, we have next talk. Okay, always here. Thank you.